So, Ayan, over to you.
Okay. Thank you, Shayan, for this kind introduction. Let me share the screen first. Yeah, so here. Yeah, the screen is visible now.
Yes,
Yes,
your
sir.
screen is visible. You're audible.
Okay.
All is good.
Okay, thank you. So thank you all, and thanks to the organizer for giving me the opportunity to talk here. This is a very exciting activity which ISER Kolkata is doing regularly, this conference, and this actually connects all the blocks of the quantum technology. So here today my plan is to talk from the direction of cold atom physics, as in the previous talk was focusing, and there were some interesting questions were there at the where it is what are the fields it can be used, this ultra cold gases. So I read long back that ultra cold gases are considered as the biggest testing ground for condensed matter physics, and as the speaker rightly pointed out, all the important condensed matter experiments are already being mimicked using ultra cold atomic gases because of its great tunability and controllability. But actually, it doesn't stop there. There is much more things beyond to it. And today I have planned to focus some aspects of that. And in that process, I will also have planned to focus a little bit on what we were doing at Bennett University. So let's move ahead. So this is what the overall plan of the talk. First, I will talk out, since here I know that there is a good section of participants, students. So I will try to spend a little bit of time on very basic fundamentals. And then from there, I will try to slowly move on. So at the very beginning, I always like to start any talk with this slide. So this slide, the cartoon was actually came in science in 1995, after first time the Bose-Einstein condensate was observed in ultra cold atomic gases. But the idea, whatever I have pointed it out here, what actually emphasizes, which also motivates me, and I like to convey that there is always a competition between experimentalists and theories. And this ultra cold gas research, the superconductivity, that Bose-Einstein condensate, this is a very good example that how each one complements other. So for example, superconductivity was first observed experimentally in 1911. And Bose-Einstein condensate was predicted theoretically in 1925. The theory of superconductivity comes in 1957, whereas experimental observation of Bose-Einstein condensate for weakly interacting atoms comes in 1995. So in some case, theory comes first, some case experimental observation comes first, but both complement each other beautifully. So then when we talk about ultra cold gases, just as a small recap, what do we mean by ultra cold gases? So it is a very, very cold temperature, and at the end, as our chair of the session was also mentioning, till which temperature we are able to gone down about picokelvin, we have already been able to. So there is a basic fundamental difference, which I like to point out here, where something called cold atom, something called ultra cold atom. So cold atom, till cold atom, we can actually use Maxwell-Boltzmann's distribution. However, when we go to ultra cold gases, we have to use, for bosonic species, we have to use Bose-Einstein distribution, and other cases in the other Fermi-Dirac distribution. So this temperature is about 0 Kelvin, nearly 0 Kelvin, but never 0 Kelvin. So here it is written 100 nanokelvin, or it can now go much beyond that. So at this temperature, the atoms, the quantum mechanical properties becomes very important. And to reach this cold temperature, you require a lot of technologies. And that was the sole reason it took 70 years from 1925 to 1995 to actually observe the Bose-Einstein condensate. There, it required a lot of technical advancement in trapping, in cooling, and for today's talk, I am not going any details of those, but we will try to focus on something else. So, but before going in something else, what I feel is always important. This is specifically intended for the students. When I say ultra cold atomic alkali gas, why alkali? And what do I mean by Bose-Einstein condensate, bosons, fermions? So the main primary reason here, I have taken this picture from the Pethick and Smith's very famous book on Bose-Einstein condensation, which shows that these alkali atoms, hydrogen, lithium, sodium, potassium, rubidium, cesium, they have an outer shell of 1 electron, which makes it a very good candidate for Zeeman effect, and therefore they are very sensitive to external magnetic field. So using external magnetic field, it becomes much easier to trap them and control them. Now, when we talk about Bose-Einstein condensate, we talk about boson. We know that bosons have integral spins, fermions have half integral spin. But here, what do we mean by what is the condensate of? That condensate in general, we define the boson or fermion, it's based on its neutron number. So if neutron number is odd, then it is a fermion. If neutron number is even, then it is a boson. For example, lithium-6 is a fermion, and its isotope lithium-7 is a boson. Okay, so these are very few fundamental things. Now moving ahead, as the title of the talk promises, that I have planned to talk about atom interferometer. So what do we mean by interferometer? So the students are already exposed to the basic ideas of interference. Now here, we talk about a material counterpart of, you can say, Mach-Zehnder interferometer. So what is Mach-Zehnder interferometer in general? So I just want to give a very brief description of a Mach-Zehnder interferometer. This is fundamentally, it's a very rough description. Please be aware of. So you have a beam splitter which splits the beam in 2 halves. Then we have 2 mirrors, and that mirrors, the splitted beams gets reflected from these 2 mirrors. And then I have another beam splitter which actually combines these beams, and these beams, now because of different paths, they can have a different path difference, they can have a corresponding phase difference, and they can lead to an interference pattern. Now, when we have an interference pattern, we know that there are a lot of, it becomes, in optics, it's a very important issue, and we can study things in a much more detailed way. Because at the end of the day, interference experiments gives us a very precise and very, very fine measurements. So for example, when in the late 1880s, there was Michelson-Morley experiment, Michelson interferometer. Why it was so? To get ether, to prove the existence of ether, how we can prove? So there again, it was assumed that if we can use an interference properties, it is possible to get the signature of ether. It was not there, of course, and it is considered as one of the most famous failed experiments. But that is how I try to emphasize to the students that interference experiment is very, very important experiment, which gives means a very fine level, a high precision level of measurement. So what atom interferometer we want to mean is something like here we consider this is some kind of a role reversal. So here in the previous slide, you can see there were some beam splitters. These are some materials. And then you have light. And you are doing some experiments. You are studying interference. Now in atom interferometry, what happens? The position of light is taken by matter and the position of matter is taken by light. What do I mean by that? These beam splitters and mirrors, they are actually referenced as some kind of a laser pulses. Say the pi pulse is considered as analogous to mirror and pi by 2 pulse is analogous to beam splitter. So what happens? So this one serves as beam splitter and this one serves as my mirror. So the first pulse serves as a beam splitter. So I have a wave packet and it splits that wave packets in 2 parts. And then the second pulse serves as a mirror. So it gets reflected, and the third beam again acts as a beam splitter that recombines the 2 trajectories so the interference can occur. This is the interference of the matter, which we know it is possible. From de Broglie's theory, you already know matter has a wave property. So we are exploiting those ideas. When these paths differ in height, so here there is a height and this is actually in real space, this path difference is happening. And there is a velocity gradient. So we can actually, using Newton's laws of motion, we can calculate the trajectory if there are 3 points are there using S equal to ut plus half ft square kind of formula. We can actually get some expression for the x. And in interference, we measure phase. Now the phase we measure, you can write as some kind of e to the power of ikx. So if you know x and you know phase, you can actually, there is phase, actually phase you can measure. And from there, you can conclude actually about the acceleration. So your x is a function of gravity. Because you know just simply s equal to ut plus half ft square or half gt square. So g is there. Now you know g, you know x, you can measure by interference study, you can get phase, the k is a wave number, you know, then from there you can get this g. And this becomes this interferometer now can be used a very sensitive gravity sensor. Now it comes to the point some of you have asked, so where we can use it. So as it becomes a gravity sensor, it has a huge scale of applicability. Say we can do precision measurement on atom interferometry and atomic clocks. This can lead to understanding of even dark matter and dark energy, apart from precise measurement of physical constants. Then accurate measurement of gravity is very important for geophysical research to detect tectonic shift or underground water movement. Then there is atom interferometer for inertial navigation. So that is some kind of a ultimate idea, you can say, that with the cold atoms, if we can make some inertial navigation systems. So you can detect oil and minerals also. You can apply in the civil engineering purpose in space. So it has, when it becomes a gravitometer, it gives a very precise, exact measurement of gravity. It becomes a very, very useful tool. And the current quantum technology section of the current quantum technology is actually dedicated towards this side. So now let's come to the next part of the talk, where I would like to talk about quantum liquid and something on binary BC. So what we were doing, and then at the end, I'll try to connect it with this idea of atom interferometry, and whatever the small steps we made towards atom interferometry, that we will try to get back. Okay, so what happened in 2015? Petro proposed an idea that you can create a quantum liquid state starting from a mixture of quantum gases. So liquid state, what it means, it is something like some cluster of atoms, and it creates some sort of a liquid. But what helps to make this cluster? So in atomic BC, from atomic BC, you construct a liquid-like state, and what makes this cluster of the liquid formation, what is responsible for it? For that, Petrov suggested that in the energy functional expression, when you do the Born approximation and energy, the interaction energy we calculate, in general, to describe the Bose-Einstein condensate, we are happy with the first term. We do with that, this gives me in the usual Gross-Pitavsky equation a cubic nonlinearity, and we are working with it for quite some time. But Petrov's idea was that for liquid formation, you need to take the second order correction also. When you take that into account, that will help you for liquid formation. But this term was actually proposed that also long back in 1957 by Li, Huang, and Yang. So this is many times known as LHY correction. So in general, then the question comes, why till now we haven't talked about these terms? Suddenly, last 4, 5, 6 years, we are talking about this. The reason being is that this term is fairly small, does not make any substantial contribution in the regular studies, experimental studies, which is been simulated using Gross-Pitavsky equation. So it was not making much of a big difference. So therefore, it was not considered. But now the situation is that if there are many mean field contributions, there are different mean field contributions, and maybe there are some other interaction contribution which nullifies the mean field contribution or makes the mean field contribution very small, then it may happen that this beyond mean field contribution will start dominating the picture. So with this, actually, then came in 2018 the experimental observation. So here you can see that energy, and this axis is my density. Now this is my LHY correction, this is my mean field interaction energy, and this is my LHY interaction energy. If both are repulsive, it's fine. But now, if my LHY, my mean field interaction is attractive and LHY interaction is repulsive, then there is a competition between these two interactions, and we can have a non-monotonic energy function. And this is where actually the suggestion of liquid formation came. So this is again observed in BEC mixtures of potassium-39. And also this was followed by observation of transition of bright solitons in through quantum droplets. So these were also observed. Okay. So as we were talking about binary BEC. So how to model the binary BEC? This is a very standard coupled Gross-Pitavsky equation. And here in this, there are this A11, A12, these are your, these A11 and A22 are the intraatomic interactions, and A12, A21 are the interatomic interaction between the two components. So now, if there are these two components do exist, there can be different kind of mixtures. So these are, in many cases, these are two different hyperfine states. So there can be a situation which is called immiscible, where they are not much mixed. There is some sort of a separation between them. And there is another situation can be which is miscible, where the two states or the two components of this binary BC, binary Bose gas, they are mixed. Now, you see there are different interactions in the game. There is G11, G22, which are intraspecies interaction. Then there is G12, which is interspecies interaction. Now, if G12 is greater than the square root of G11 and G22, the states are phase segregated, hence the system is miscible. That is, I want to mean this region. Now, if the interactions holds this condition, then the condensate overlaps, and this is called the miscible region. Now, if the condition follows this, the interaction picture condition follows this, then the attractive interspecies interactions overwhelms the repulsive ones on each condensate, and the system collapses. Now you see, if I take this side term, this side, and I consider there is a small difference, something called delta G, where this delta G can be defined like this, and I consider my delta G goes to 0. So this delta G is very small. So in this situation where these all mean field interactions, because of their competition, they become very small and they contribute. Then in this point, actually, it becomes very small, and the beyond mean field interaction starts playing an important role, and we see the formation of the droplets. So if we come to the model, actually what we were interested, we consider something like a sugar-shaped model. But before going there, say I want to consider a quasi one-dimensional system, and there this two-component BEC equation can be reduced to an effective one-component equation when we assume that they have identical spatial modes and the equation, and this is my beyond mean field contribution. So the interesting part here is that this beyond mean field contribution gives me a quartic nonlinearity. This is the regular cubic nonlinearity, which is already present in Ross-Pitavsky equation. This is a new term. So when we were studying this, we realized that already there exists, Petrov also did a calculation in the lower dimension. So, and in that 2016 PRL paper, Petrov suggested that if we were for Bose gas, please remember in 1D, we don't have BEC, but in a Bose gas, I can write an effective equation of motion where there will be a beyond mean field contribution, but that beyond mean field contribution is, this nonlinearity is quadratic in nature. So this quadratic nonlinearity here, the signature what we get in one-dimensional system as per Petrov's calculation. But if we start from a three-dimensional system and do a systematic dimensional reduction, we can land up to another equation which we can see a quasi one-dimensional system where we have a quartic nonlinearity. So you see there it is a very interesting region, the interesting part here. You observe that in 1D, my cubic nonlinearity is repulsive and quadratic nonlinearity is attractive, whereas in quasi one dimension, my cubic nonlinearity is attractive and quartic nonlinearity is repulsive. So how to reach to the quasi one dimension. This is actually more experimentally amenable. You create a Bose-Einstein condensate in a three-dimensional trap, and then you squeeze in a transverse direction, and you elongate the trap, so you can get a Bose-Einstein condensate in quasi one dimension. So this is the interesting difference was there, and we have pointed it out, and we tried to solve this. The trouble here is that there was no previous literature available which discusses a cubic and quartic nonlinearity. So an odd and even exponent of nonlinearity and its analytical solution, this was never been discussed. So what we tried, the first way what we tried, let's take a very generic problem. We treated, is it more of a mathematical model, equation which has some cubic nonlinearity, some quartic nonlinearity, has some potential. We tried what kind of solution, whether we can get, we were looking at that. Because already we know that for cubic nonlinearity, there is a conoidal solutions are available. So we cannot we can consider these conoidal solutions as a starting point, and we can move further ahead. So we took conoidal solution, and we did the calculation, and from there we were able to get some solution in the as a function of conoidal functions. So they come like this. The red lines are actually describes your the trapping potential, and the blue dots are the solutions. So we obtained the CN solution, we obtained SN solution. So what the message we got from here? What we find that these conoidal solutions do admit localized modes. I can see this, there is localized modes, but do not admit sinusoidal modes. So when m is equals to 0. Now also we can see that Cn the solution does not exist for m equal to half for Cn case, but for Sn at m equal to half we can have a solution. And for Cn m equal to 1, we can get some bright soliton and W soliton like structure. And for Sn m equal to 1, we can get kink anti-kink pairs. So these are some ideas we obtained for a cubic quartic nonlinear Schrodinger equation. So then we proceed to actual physical system to tackle, as I have said, these are three-dimensional equation with proper trap management. We can reduce it to a quasi one-dimensional equation. So here with these unsaged, we can actually reduce to this type of a quasi one-dimensional equation. Now here, this is my trap term. This is my usual cubic nonlinearity, and this is my new quartic nonlinearity. Now for my convenience, for my analytical convenience, for the time being, I consider K going to 0. Or I am considering the longitudinal trapping is also very weak, and it is nearly 0 for the time being. I will come the other situations little later. So with that, I took an unsaged solution, I inserted it, and I got certain conditions. And at the end, I was able to get a solution, but this solution is quite restricted. And it says that at if the mean field and beyond mean field interactions has this type of a relation, then only I can have an analytical solution. Then we made some study of the stability and those things. And after studying stability, we realized that this solution corresponding to this condition is not stable, while solution corresponding to this solution is stable. So this solution is more stable. So this is a stable solution. This is an unstable solution. And corresponding means particle numbers we can calculate and all these things. Okay. So this is what we learned for a actual cubic quartic analysis. Now we physically try to describe this. We calculate the effective mean field energy, effective beyond mean field energy, and this interaction potential. I described this is my interaction potential. We calculate the equilibrium density by equating the pressure to 0, and we get this as some 6.25, and which is actually matches pretty well. Here, if we go, this is my equilibrium density. So you see this from theory, I get this is 6.25, and from my solution, I get it something like 7 and 8, something like that. So there is a much better match, pretty good match. Now, when we try to calculate the critical density, so effective interaction energy functional is 0. We set it at 0. And we get critical density as 14.06, which actually matches very well here with my solutions. So what are the takeaways from here? This study, we realized that there are 2 analytical solutions, and then one solution is unstable, one is stable. Then the solitonic droplet regions, what we discussed, calculating the critical and equilibrium density. So the region behind, so here the soliton formation starts from soliton, the droplet formation starts, and after that again it goes back to the solid. The droplets again starts breaking down and it becomes again soliton. That signature we will see in the next study. So the soliton droplet regions are discussed by calculating the critical and equilibrium density, and unstable regions under modulation instability points to the low density region where bright soliton formation takes place. Well, now what we do, as we have said, that here I have taken K going to 0. This was for the convenience, analytical convenience. But what will happen? But numerically we can solve it for K not equal to 0. So we did next the numerical study, and we numerically solved the extended Gross-Pitavsky equation with quartic nonlinearity for different K value. And interestingly, what we realize that if we modulate with this K, that way also we can move from droplet to soliton region. So if K is very weak, then I can see a droplet formation. And if we start squeezing the longitudinal trapping frequency, there is a sudden change from droplet-like state to a bell-like state to a soliton-like state. So to understand it further, we calculate the chemical potential and energy, and we see that in this region, so this is my droplet region where I have negative chemical potential, negative energy, and then it's progressively moves, and this is my K, the longitudinal frequency square term, and this region here it moves smoothly, though not monotonic, but it moves pretty smoothly, and the energy and chemical potential becomes positive, and we conclude that these are the region of the soliton region. So it moves from droplet to solitons by tuning the trap frequency. This becomes more evident when we study the droplet size. So as a droplet, it has the size is much bigger, and we put the droplet. So when we normalize it by x0, the droplet, the base size, so it is 1. And as we tune the trap frequency and make the longitudinal trap relatively stronger, we see that the size is dropping, but this drop is pretty smooth. So this suggests that this is some sort of a crossover, but not a phase transition. So it's not a droplet to bright soliton phase transition, but rather a droplet to bright soliton crossover, we can say. And we also studied the peak densities, and so this N0, so so this N0, you can see the peak density remains constant. If this is for a liquid, this peak density remains constant, and after a certain point here, it starts increasing the peak density. So this is actually nothing but explaining this feature. So peak density remains constant, and after a certain time, it increases. So here all the peaks are same because it is normalized by N0, that is the at X0, that at center point density, it is normalized by the center point density. Okay, fine. So far, this is what we understood. So from here, what we learned that tuning the longitudinal trap frequency, we can observe a droplet soliton transition. The transition is smooth, thus not a phase transition, rather a crossover. And droplet soliton phase diagram as a function of trap frequency, strength, and particle number we have prepared. So this is with particle number, and this is trap frequency, strength, and you can see, so this is, you can say, the phase diagram for the peak density. And see, you see this region, the peak density, high particle number, it increases, and this is actually, so it moves to into the solitonic region, and here you see that peak density more or less remains constant. So this is the region, the droplet region. Okay. So let us now come, we were talking about, we actually diverged from the point here. We introduced this equation. We talked about 1D system, but after that, we concentrated on our approaches, which is a quasi 1D system because it's more experimentally amenable. So the study was more on this. Now we go back and try to look at this 1D system whose solution was already exist, but we are interested to study these droplets emerge from this 1D system. If they are subjected to some impurity, how they behave. So that was the objective. So what we do next, I hope I'm able to explain the objective. So after a certain amount of study on the quartic system, cubic quartic nonlinearity, I am going back to quadratic cubic nonlinearity. Just in the mathematical term, it is like that. But in a physical way, I was in quasi one-dimensional system. Now I want to move to a 1D system where I want to study the response of some impurity, response of the droplet due to some impurity. So if this impurity potential is absent, the analytical solution was already known and proposed in 2018. So this is the analytical solution, and if you can solve, the solutions will look like that. This is in terms of different particle number. Now, what we consider? We consider an impurity potential of this type, and it can be a potential well, it can be a potential barrier. For here, actually, in our submitted work, we just recently submitted this work. So there we have discussed the barrier and well both, but since well gives more interesting features, so here for the timing, I'm concentrating more on the well. I am not concentrating on the barrier, but if you want to get more details about the barrier, you can get it from here. So the situation, so you have in the landscape, you have a potential well, and said the droplet is moving with some velocity k. based on these V0, based on the how deep the well is, we can see how the droplet will behave. So here in this case, you see if V0 is some, the value is something like minus of about 0.248, we can see that there is, this is my droplet, it encounters the potential well, and there is a fragmentation. And due to this fragmentation, one part gets reflected and one part gets transmitted. If you keep this V0 further small, actually you can see that full transmission. Now, if you increase this V0 a little bit more, where this V0 is something like minus of 0.3, things becomes further interesting. You see some reflection, you see some transmission, and you see some trapping. So some part of the droplet gets reflected, some part of the droplet gets transmitted, and some part of the droplet gets actually trapped. So we can do bifurcation of these quantum matter or this quantum liquid using some potential. So here we actually, therefore, when we talk about this reflection transmission, definitely we must study the reflection coefficient, transmission coefficient. So this is my transmitted beam over the time. This is my reflected beam, and you can see they actually, if we add them, they actually conserve. Now here, and in this picture still, this orange line is actually trapped beam. This is the trapped beam, and this trapping potential, this is almost zero, we can see. Now, for this case, we can see a very minute trapped mode again, but this is means very minute. So we actually magnify the trapped mode and see, of course, these are some non-zero amount of particle number we see in the trapped mode. Here again, this green line talks about reflected beam, the blue line talks about the transmitted beam. So how we calculate, this is how we calculate the transmitted norm, this is the trapped norm, and this is my reflected norm. And we take a snapshot, time snapshot of this, of quantum droplet colliding the potential well of depth V0 for V0 equal to 0.3 at t equal to 100. So at t equal to 100, the droplet actually collides almost with the potential well. Now at t equal to 300, at that time, so there is some fragmentation starts, and here you see at t equal to 800, you see a trapping part, you see a transmitted part, and you see a reflected part of the wave. So this way we can actually see the breakdown of a droplet. So now it comes, why I started with atom interferometry. So whenever we talk about interference, we talk about waves, we say, we know the first thing comes in the class when we go to talk about interference. We talk about throwing stone to a pond. We see the water waves. Now here I have some liquid, and I have some technique to break the liquid and play around with its reflected, transmitted parts. So these are in for a potential well. And what happens for a potential barrier? Potential barrier, we have seen that it becomes more of a reflection and transmission, or trapping we didn't see much. Now you will ask me why we are not talking about cubic quartic analysis, that in quasi one dimension. So we had started working on that quasi one dimension also, but results are still a bit, it's more sensitive, numerically very sensitive. It is showing. So we that work is still under process, and we can have a more detailed in future, hopefully, detailed study of in 1D and quasi 1D what happens. But already, actually, we have made some study of with the beyond main field interaction. If there are solitons and they encounter this kind of barriers, how they will respond, that also we have recently submitted for a publication. That is also in the archive, and just about 2 weeks back it has been submitted. So we expect the response of quantum droplet will pose new direction for the development of matter wave interferometry. So now let us summarize in general what we have discussed till now. So we discussed the possible application of atomic interferometry in diverse technological domains, discussed recently observed exotic liquid phase in ultra-cold bosonic systems, derived quasi one-dimensional cubic quartic NLSE describing liquid phase, discussed possible conoidal solutions, derived exact analytical solution for CQ NLSE, and analyzed the droplet phase. The soliton droplet phase diagram in quasi one-dimensional geometry also we prepared, and we investigated the droplet dynamics when it is subjected to an impurity. So with this, I also like to thank the collaborator, Dr. Argha Devnath, visiting faculty at Bennett University, Professor Saurabh Bosu at IIT Guwahati, and Professor Boris Malomed at Tel Aviv University. Also, I'd like to thank the funding agency, the DST SERB, Core Research Grant, and thank you all for your attention.
Thank you for the wonderful talk, Ayan. We're ready for questions now. If you have any questions, please unmute yourselves and ask. So maybe in the absence of others asking, let me just start the ball rolling a little bit. So this is a very interesting work and on these droplets, which I think is very interesting. I was wondering if you are thinking something along the lines of dynamics in these systems, because if you think about normal both gas dynamics using GP, a lot of interesting stuff that has come out in the recent past, especially with turbulent relaxations, things like that, when you consider benches. So I was wondering if you have something in mind.
Of course, there is plenty of room to do, because as you can, droplet is a very new phenomena. So at this moment, so first thing what we are now struggling at this moment numerically, actually, for in the quartic solution to get a, we can see the signatures of reflection and transmission, all these things, but it's not very numerically, it is not coming very clear. So we are working on that. So this is also some kind of a dynamics. We are studying the dynamics here. So these dynamics at this moment we are concentrating, and also we are also looking at the case of if there are some three-body interaction. So at this moment, these are immediately what we are doing. But as rightly you have said, of course, we can look into this in the near future.
Very, very interesting. Thank you. Yes. Other questions, please. So maybe we'll wait a couple of minutes. Otherwise, we'll call it a day.
Okay, sure.
So while we wait, Ayan, maybe I just have, we're always curious about GPs. So were you also thinking about these discrete nonlinear Schrodinger equation, somewhat like.
Yeah, discrete nonlinear Schrodinger equation. Long time back, I actually started working.
Right.
But I haven't done much of work on discrete NLSC, and maybe in future, of course, we can.
Yeah, actually, I was so much of the work seems to be along the lines of the normal GP.
Yeah.
And of course, once we start introducing optical lattices, we do other things. But this has always been sort of thing that I wanted to do, but primarily not been able to do because numerically expensive.
Yeah, exactly.
This,
it is numerically very expensive.
Yeah, but why?
So long back, actually, I started some work with Gentaro Watanabe in POSTECH in EPCTP. You know Gentaro Watanabe?
Yeah. Actually, I think he's moved to China now, but he used to be at Korea.
I think he went to Japan, maybe. I don't know. So long time, I'm not much in touch with him. Actually, we started, but then due to some, actually, I was in a transition that time from Korea to India, and I was not been able to pay much time there, so I had to stop that project actually. So after that, I didn't get enough time to go back to that those calculations.
Right. Actually, there was a time this DNLSE where start off with an ansatz, much like one of the ways one does GP, right? You start off with the ansatz and then you're optimizing. But my interest has been sort of some time to get back to this and do an actual time evolution in the system with discrete because this will be actually it's a non-linear equation time evolution. So this can be an pretty interesting what's that kind of dynamics that arises.
But yeah, I presume it will be numerically very expensive.
Yeah, I think so. I think it's numerically very expensive. So that's why I know the goal would be, I guess, some sort of and see what can one do. There are some seen where people have tried discrete nonlinear Schrodinger equations, but seems to be quite interesting. But
Sure.
been able to do it myself.
Yeah.
So no questions. Any questions? Okay. If not, thank you so much.
Thank you very much.
Yes.
Yeah.
So thank you for joining.
Okay, let me stop sharing now. Yes. Yeah. Okay.